Recording is rolling. It is Friday, August 30th. So what I want to do today is help you guys out with this page as much as possible. You guys know you've had this for a few days. I've already solved a few puzzles on this. Right? Also, don't forget the graphs on the back. Did I yesterday help you guys with some of the graphs get started? So remember, actually, let's touch on those first real fast, right? And then we'll go solve some puzzles here. Right? So just a quick graph review. There's three individual scenarios, and I'm having you guys make what is displacement versus time, velocity versus time, and acceleration versus time for each of these scenarios, right? Now, you guys have gotten a number of posters and slides and thumbnail notes that have these type graphs, X versus T, V versus T, A versus T for different type scenarios. In fact, I bet some of these are going to be pretty much identical to some of those graphs you guys have already seen on your slides, right? And now the second scenario is like two parts, right? The car speeds up and then hits the brakes and it brakes to a stop. So two parts. But I wonder if you guys have a poster for the first half of that story and also another poster for the second half of that story. And then can you piece together what does X versus T look like for that? Because you have V versus T. Right? And what does A versus T look like? We'll leave a little bit open. So have you guys do some critical thinking, see who can figure this out by Tuesday, right? In this very last scenario, there's also some numerical questions. I wanted you guys to make the connections between the graphs and the equations, put it all together, what the numbers mean, what physical properties. All right, okay, so you guys set so far? All right, so back over here, I'm gonna kickstart us off with number 9 and number 10, who's been a pretty good example so far. All right, and then I'll see if you guys have a request after this. Okay, so you guys know we're starting number 9, number 10. Okay. All right, so most of these puzzles, you can just pull out these three kinematic expressions, go equation shopping, and then solve one variable at a time. Did I tell you guys which one of these puzzles is actually easier to solve with a graph? Which one? Yeah, you guys remember number 19, number 20? Actually, I got some notes here. Let's throw this up here real fast too. Okay. Here, get to review this very last one real fast. Number 19, number 20. I told you how much time had passed, how much distance, and final velocity. The fact that you did not have initial velocity or acceleration, you have two unknowns there, same two unknowns there, same two unknowns there, right? But you can solve this really fast with the graph. If you know, okay, so here's a velocity versus time graph. Here's a scenario breaking to a stop with the numbers that I gave you. If you know what is the area of a triangle and the slope of a triangle and what physical properties those represent. Guys, on a velocity versus time graph, what does the accumulated area under that graph represent? What physical property? Distance, how far, right? Because speed times time can be distance, right? And if it's a variable speed, it's just the area under the curve, right? And guys, what is the rate change of velocity called? Acceleration, which of course is the slope of a graph on V versus T, okay? So yeah, so if you set the graph on that one, it's easier to solve. Right, but yeah, let's hit number 9, number 10. So what we got here, we got a ball is thrown straight down with some initial velocity from a tree house that's some given height above the ground. Ooh, right? Let's get a picture going. So here's number 9 and 10. Number 9 and 10. Right? So we got ourselves a tree and a house and a tree house. All right, got the ground down here. And I gave you guys some values already. Like I told you, the height of the treehouse. Now I'm looking at my treehouse. My treehouse is 5 meters tall. Your guys' treehouse is probably something different. That's right. Just pick a random paper. Now X could be general displacement, but a lot of times I'll call it H for height. Okay, so I'm going to use H for height, but you guys know that represents the displacement. So it's going to be some number of meters. 5 meters for me. My treehouse is 5 meters up. Right? Hey, you guys did the same thing yesterday with like dropping the roller and catching the roller. So well, that displacement was actually a height change, so that's what showed up on your summit. I'm going to reach out the treehouse and throw a ball straight down at some initial velocity. And yeah, I did give that to you. So my paper says 3 meters per second that I threw that. So I'll go ahead and write that here. 3 meters per second. Check that straight down. Okay. Guys, what's the only planet that has tree houses on it? Earth. Yeah. So even if I didn't explicitly type this number, you could probably figure out that the acceleration is Earth's gravity field. Gotta call that, well, on this paper, I used 9.8 meters per second squared. So I'll do that also in the notes, just so that your answer choice is going to exactly align with these notes, right? More often than not, I'll round that number to 10 meters per second squared, but I guess not for now. So there's two things that we could find. I could say, how much time does it take to reach the ground? Because there's some exact answer to that. It's great, right? If I'm on Earth, I check the ball down that fast, treehouse this height, it's got to reach the ground in exactly some amount of time. We're going to solve that. Okay. Also, the other thing I can find is what's the crash speed? I call it V sub f, like final velocity. Right? And this is a little Liz marks here. Right? Like 1 millimeter above the ground. Right? It's about to slam into the ground. How fast? Right? You guys got all that? Okay. All right. So with all that, here I'll circle this one too because that's the other thing I'm searching for. Okay, so see, I know V naught, X or H, and G, and I don't know VF or T. Okay, so with that in mind, let's pull up these kinematic expressions. Somebody nominate one of those expressions. Which one do you guys want to start with? First, second, or third? Okay, I'm hearing a nomination for the first one. All right, so let's see if that would work. Okay, so I know the height of the treehouse. Bing, we're good there. I know the throwing speed. Bing, we know that. I know this acceleration due to gravity. Bing, got that. And I don't know the t. Could I use this to solve it? I think I could, right? Now, weird thing is, guys, this one's gonna be a little tricky because what I'm solving for is being squared here. It's not being squared here. And also there's gonna be some other constant thrown in the mix. That means you're about to run into what situation? Starts with a Q. Quadratic. That is quadratic, isn't it? Right? Tell you what, I do want to do this with you guys. But I want to come back to it because there's a little bit more I want to say about it. Right? There is a maybe a little bit faster way to solve it, I think. Oh, can you guys think of it a different way? Let's do this. Here's what I'm gonna do. So let's do forest for the trees type road map. I'm gonna pick this third. Yeah, we'll come back and we'll definitely solve it that way too. Right, so I will do that. Right, all right, promise you guys there. But here's what we're gonna. I'm gonna pick this third one because you know the throwing speed, the acceleration, and the height of the tree, so I can figure out the crash speed really fast. Right, crash speed, and then I'm gonna take that crash speed and pop it into the second one. Now I know bing, bing, bing. I know these three, and then I can solve for the time and I can get it that way, right? That's a different way. Again, whether you only do the first one or you do the bottom two in conjunction with each other, you should get the same answer. And I want to show you guys that, in fact, that will be true. And then a little bit more to say about that too. So let's do that as a roadmap. So let's go final velocity squared equals initial velocity squared plus 2ax, right? So there's our setup. Right? So here's what I do too is I'm going to split the paper and solve this a little bit two different ways. Okay? One way is I'm going to solve this in terms of variables. I'll do that over here. So the crash speed, we're solving for that first, right? Squared is equal to the throw speed squared plus 2 times, hey, guys, acceleration, just to get you guys used to different terminology. Is it okay if I call it acceleration due to gravity? Because it is, right? And the displacement, can I specifically call it the height of the treehouse? You do that too, right? Oh, speaking of which, I meant to emphasize this point. Oh, I'm going to define down as the positive direction, and then very conveniently, all the numbers are positive because the ball moves in a positive direction. So that's like a positive height going down is positive. Gravity is pulling down, so that is allowed to be positive. My throw direction is down, so that's allowed to be positive. And the crash velocity is also down, so that could be positive. So everything's down, which is all positive. Right? All right, so I got all positive numbers. On the right, I'm going to go ahead and pop in my numbers, or at least the ones that I know. I'm still solid for final velocity. I know my throw velocity on my paper was 3 meters per second. Okay. Now that's going to be squared. Then I'll say plus 2 times this acceleration could be 9.8 meters per second squared today. And then the height of the treehouse, I have 5 meters. 5 meters. So Boing, boing, boing. See that? Okay. Guys good? All right. So, and you don't have to do both ways, but you do either way. I want you to be the same way. Oh, it looks like actually I only have one algebra step anyway. I have to do what to both sides? Square root. Do square root. So final velocity is going to be the square root of the throw velocity squared plus 2gh. Okay. What's nice about solving in terms of variables is that you get everybody's answer. You guys know there's like 10 different versions of this paper floating around with all different numbers on it, right? But it's all the same scenario. So this right here, what I just boxed in, is the answer to everybody's paper. Okay? You can plug it in and it'll work. Now over here, if I plug in numbers first, that's okay. You do that too. All right, I need to check this down to smaller steps. So what is 3 squared plus 2 times 9.8 times 5? Okay. So I'm getting final velocity squared is equal to 107. Now this would be meters squared per second squared. If you keep track of the units. Okay. Then I have to, square root. And I just, maybe I'll do that in pink. Yeah, square root both sides. Therefore, can I do this? Can I do second square root, second answer? Okay. Well, here, I'll put in 107. Do that. So it's so the crash velocity, how fast is it slamming into the ground, is 10.3, I'll call it. And then the unit also gets square rooted. That gives me meters per second. Okay. You know what, too, is I'm going to, right beneath that, a bunch of extra digits. It's really more like 10.3441 meters per second. Okay. Now, realistically, you could never really know that level of precision, right? We don't have that many digits significant to start off with. Right? But the reason I'm keeping a bunch of extra digits is because I'm going to carry this number over to another expression. That's to say, this middle term right here, and then solve more stuff. So if you save your rounding for the end, then like if you have a multi-step problem and you keep rounding along the way, then your numbers kind of might deviate more and more, and you get kind of spreads away, right? But if I save a bunch of extra digits, then everything tends to be pretty spot on. Right? Let me show you guys that this does work over here. So if I plug in this, a giant square root, so I'm doing this general expression, my throw speed was 3 meters per second. So I'll do 3 squared plus 2 times this 9.8 times the height of 5 meters. I should get the same thing. And it is. It's the same thing. Right, guys good? Good? All right. So now that we know the crash speed, we can go back and find the time using this guy right here. Right? Use that and solve for the t, solve for the time. Right. That's it. That's the next thing I do. We go final velocity equals initial velocity plus acceleration times time. I'll do the same thing. I'm going to split the paper so you guys can see 2 different ways to do this. Okay. I try to get my AP kids especially to solve in terms of variables. That's a good skill to have. Okay. But if you want to plug in the numbers first, that's all right. Okay. I could go G, and then I'm solving for T. Okay. And then over here, I know the crash velocity because I just found it. I'm going to keep a ridiculous number of digits. Because that's that number right there. I know my throw speed was 3 meters per second. And then it's picking up at 9.8 meters per second for some time. Okay. Just like that. All right. So say if I was solving in terms of variables, I would subtract over this v naught. So final velocity minus initial velocity equals gt. Therefore, final velocity minus initial velocity, all divided by the gravity field, is how much time has passed. Okay, so there's like the general master answer that's true for everybody's paper. Right? And how about my specific numbers? What if I plug in the numbers first? What would that? Subtract. Oh, maybe I should ask you guys. Guys, what's the next algebra step? What's my next algebra step? Yep, subtract 3 meters per second. Guys, what's 10 minus 3? 7. And then I got all this change right here. So, right, and that's meters per second. And that's equal to 9.8 meters per second squared times however much time. That was fine. Okay. And what's my next algebra step? Should I subtract or divide? Divide. There you go. So let's go 7.3441 meters per second divided by 9.8 meters per second squared. That's what the answer is going to be. Okay. Let's get a numerical value. 7.3441 divided by 9.8. Okay. So that is, all right. Now we're getting the answer. We finally got the answer. 0.749, 0.75, right? That's probably as precise as I could realistically know. Okay. And, oh, and guys, what's the unit on that number? What's the unit? Seconds. Okay. And there's a few ways that you know that. One is that, well, that's going to describe time, right? Time is measured in seconds. Okay. Another way is look at here, I cut my units all along the way. What is meters per second? Here, I'll just meters per second divided by meters per second squared. Do you guys see one fraction divided by another fraction? As if you have one fraction divided by another fraction. What's the rule? Can you take the bottom fraction and flip and multiply? You guys remember that? Flip and multiply? So that's the same thing as meters per second multiplied by seconds squared per meter. And I'm left with just seconds. Aha! There it is right there. Oh, top level here. Right? Isn't that okay? Right. So I'll write down t. It actually equals 0.7494 seconds. All right. So in case I need the precision for later. Okay. You guys all right? All right. Because the first equation nomination that you guys threw at me was, hey, what about the first one, which you could totally do. And I want to show you guys that this is going to work. Okay, you guys ready for this? And you guys said it was going to be quadratic, didn't you? Because we're solving for t and we're going to know everything else. T's being squared, the t's not squared, just a constant in the mix. Yeah, this is definitely this guy right here, isn't it going to be? Right, we just got to make it look like this format, like set equal to 0, and then it'll be pre-solved for us right there. Quadratic format. Let's try that out. I went that way with it. So shuffle this over. So here's my general x equals b naught t plus 1/2 a t squared. Boom, on the board. Okay. Now this x, I'll go ahead and plug in everything. Okay. So this x is the height drop, so the height changed. So move down 5 meters. That's in the positive direction. I'll call this positive 5. No, it would be meters. A little unit there. Is equal to the throwing speed I gave you. So my paper says 3 meters per second times t we're solving for plus 1/2. Acceleration due to gravity. That's 9.8 meters per second squared times the time we're again solving for, but this time squared. You guys get that? Okay. I got to rearrange this to be in this quadratic form. Because if I can get at squared plus bt plus c is equal to 0, then t is equal to that whole quadratic formula right there. That's what we're about to do. So half of 9.8, is that like 4.9? So let's go 4.9 as units, t squared plus 3 units times t. I have to subtract over the 5 meters. Okay, so now we're getting a negative sign in the mix. Don't miss that. This is 5, this is meters. Now this is all equal to 0. Is that all right? All right, so let's do quadratic. T equals, we go, this is like A, B, and C. We got negative B. I'm going to go ahead and drop my units. Is that okay? Just to make it look like clean with all the numbers. Plus or minus the square root of b squared, so it's like 3 squared, minus 4 times a times c, which is negative itself. So guys, don't miss that there's a bunch of negatives flying all over the place now. Gotta watch your negative footwork. Got some negatives going on. And then this whole thing is divided by 2a, which is like 2 times 4.9. Okay. Yeah, I could put the unit. I could just tag it on the end. Some number of seconds. That's what it's going to come out to here. Okay. Is that right? Okay, guys good? Now, guys, the fact that there's a plus or minus means we're going to get how many answers? Huh. I think we get 2 answers out of this. So I'm going to go down here and say t equals. I'm going to say something or something. And so we'll get 2 numerical answers. And I'm going to, you guys see, there's a way to interpret each of those. And so now 2 ways to put this in your calculator. One way is that you could chunk this into smaller parts. Like I could put this in my calculator, write that number down, put this in my calculator, write that number down, right? You could break it into bits, right? And get to the answer. I'm going to plug this in my calculator all in one go. But to do that, you have to make sure you know how to communicate to the calculator. You have to put all the parentheses, especially where they go. So I'm helping you guys out a little bit. Because right? I've seen so many students over the years like, they know the math, they know the science, but you can't tell the calculator what they're thinking. While I'm at it, can I, guys, minus, can I just cancel those 2 negatives, make it plus, plus? All right, so here, I'm going to definitely open with the parenthesis because I have to start with the parenthesis. Here's why. I got to group the numerator all together. Right? If I don't do that, I've already missed the problem. I'll go -3, no, plus or minus. I'm going to go ahead and do plus to start with. So I'll do square root. Okay. Now, on this model calculator, every calculator is a little different. Okay. This model calculator, when I hit square root, it automatically opens a parenthesis. As soon as I close that parenthesis, this calculator is going to stop square rooting. So just be aware of that. I got 3 squared. Okay, I canceled my negative, so it's plus now 4 times 4.9 times 5. Right, now close this parenthesis, it stops square rooting. Close another parenthesis, and that closes the entire numerator. So I just grouped the entire numerator together. Right? And then divide by, then open parenthesis, because there's a bunch of stuff down here in the denominator that I got grouped together. It's 2 and 4.9 multiplied together. Then close that. All right, so this should do it for me. All right, guys ready? Oh, and you know what? Before I hit enter, don't we already know what the answer is? And with my numbers, what was my answer? 0.75 seconds? Should this tell me 0.75 seconds? Moment of truth. Oh, yeah. It's the same thing. 0.75, rounding a little bit. 0.75 seconds. There you go. That could be. Yeah, that worked. I guess good. Right. But you know what? Still curious about this blank over here. What if I had done the minus version here? You guys know, one reason I really like this model calculator, I bet some of you guys know this, but maybe not everybody. You guys see the scroll keys here? Scroll keys? Because if you're ever doing multiple calculations and they're like really, really similar, but they got like tiny tweaks, like this number's different or this negative sign's different, all you have to do is scroll up, scroll over, and then in this case where there's a plus, just pop in a minus, done. That's it. You guys see that? So save you some time. Okay, I'm getting a number here. Says negative 1.36. Of course, the unit would be seconds. Right? Now, what does that mean? Like a negative time? A lot of physics teachers at this point would say, oh, well, there's no such thing as negative time. So if you get a negative time, you could ignore that one because that's not going to be the answer. I guess that would be consistent anyway because the positive one was the only multiple choice answer anyway. Right? I want to give you guys a little bit more nuanced answer than that because there is a way to interpret this. So you guys ready for this? Right. This one takes some imagination, but I want to show you guys kind of what that could mean. I'm going to do this in pink ink. I'm going to put a cannon right here. So this cannon in pink ink is going to be is going to blast a cannonball pretty much straight up. Right? I'll give it a little bit of lateral motion. You can see, but pretty much straight up, pow. Right? And the cannonball goes way up, and the cannonball comes back down. Right? So pink ink is the cannonball, and then black ink is my baseball. Right? Now, what if this cannonball blasted, goes straight up, it's falling back down, and then right as it's passing the treehouse, it's got some speed, doesn't it? Right? You chuck the baseball straight down, same time, and the cannonball and the baseball fall side by side all the way down, pow, to the ground. You guys imagine that? Okay. And then you videoed that, and now you reverse the video. Now we're playing the video in reverse. You guys see the baseball and the cannonball side by side? Right? You go up, and then right at the point of the treehouse, the baseball comes to stop, but the cannonball keeps going. It follows this path. You guys know this is all backwards in time. until it reaches the cannon. How? Right? Which is at ground level. Now, all the equations said, when is the baseball basically at ground level? And one of the answers, of course, was 0.75 seconds into the future from when you threw it. Right? Guess when that cannonball would be reaching the cannon? How many seconds ago? There you go. 1.36 seconds in the pass. There you go. You guys see that? Ah, yeah. All right. All right. So you guys good? You guys good? So, all right. All right. So my other classes, I've had time to pretty much do one more of these scenarios. I think I want to do that with you guys too. And then we'll have a spare time because this is fifth period. Got a little extra time. I can walk around, help you guys out individually too. Okay. Does anybody have a request for another scenario you guys want to see? Another scenario. Okay, I'll just pick one then. I haven't done this one yet today, but I see Alien Planet, and that looks fun. So let's do Alien Planets. You guys want to do 1718. Alien Planet. A ball is thrown straight down with a given initial velocity from the top of a cliff of given height on an alien planet. Okay. So let's do 17 and 18. All right, get a cliff. All right, I'm going to take this ball, throw it straight down, call that initial velocity. All right, well, we kind of know what's going to happen is there's going to be a cliff of some height. There's going to be some crash velocity. There's some gravitational field, which we definitely don't know because alien planet. And there's some amount of time it takes to reach the bottom, right? There's all my variables, right? My 5 kinematic variables. Boom, 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 boom. Right? So which ones did I give you? Which ones do you have to solve for? Right, so I told you the height of the cliff. My paper says 55 meters. 55-meter tall cliff. Woo, it's a pretty tall cliff. What else do I know? I know I threw the ball down at 6 meters per second, 6.0 meters per second. And I know, I know the crash speed. Okay, maybe I brought like a speed gate with me and the ball goes through and, okay, so we know the crash speed. It's like 24 meters per second. Something like that. All right, you guys got that? All right, so what's the gravity field of the planet? And how much time did it take to go from the top to the bottom of the cliff? Right, you guys get the premise? Is that right? Right. Now, before I go plug in and chugging, remember, this was a physics class, like a science type class. Can you guys sort of maybe get an idea of a reasonable number before you start plugging numbers in? Like, guys, if this cliff was on Earth, 55 meters is a pretty tall cliff. Do you guys think that on Earth, it would probably speed up to more than 24 meters per second, do you guys think? Maybe I could play around with some equations and kind of verify that, but I think that would be the case. So if this ball has not sped up very much compared to Earth, do you think this planet has really strong or really weak gravity? Yeah, I think weak, because it looks kind of slowish at the bottom. I'm going to guess this is less than 10 meters per second squared. Maybe I'm wrong, but I think that'll be the case. We're going to find out. All right, so let's see. I know the velocities and the height change. I don't know the gravity field at the time. So, guys, which kinematic formula do you guys want to start with for a second and third? Actually, there is definitely a best answer to this one. Which one do you guys think? The third one. Yes. Yes. All right, guys, here's why. Here's why. Right. Oh, well, here's why not the first two. You guys know acceleration could be the gravity field in this case, right? And we don't know that, and we also don't know how much time. So that's two unknowns in both the first one, right? But the third one, I know that and that and that. Ding, ding, ding. The only thing I don't know is this acceleration, which is the gravity field. So I can definitely solve. Yeah, that's a good choice right there. So let's go. Final velocity squared equal. This is again is 17 and 18. Is equal to initial velocity squared plus 2ax. Right. Here, I'll do this thing where I split my paper again. Split the paper. Right. Solve two ways. So one way I'll go final velocity squared equals initial velocity squared. I'm going to change my notation a little bit again. I'll call the acceleration due to gravity. I'll call the displacement a height change. Okay. On the right side, I'll plug some numbers in. So I know the crash speed was 24 meters per second. That's being squared. It's right there. I know the throw speed was 6 meters per second. That's of course also being squared. Okay. Now I don't know the gravity field of the planet, I'm solving for that, but I do know the height of the cliff was 55 meters. Oh, there it goes. Guess it. All right, so see, in terms of variables, should I subtract the initial velocity squared over first? Vf squared minus v naught squared equals 2gh. Right. And then over with the numbers, ooh, maybe I should multiply this out. What is 24 squared is 576 and some crazy units. 6 squared is 36 and crazy units. 2 times 55 is 110. That's meters. And then I got gravity field that I'm solving for. Okay, see that? Just subtract that over. So it's 576 minus 36. That's 540. And then crazy units. Okay, so now the left half of my page and the right half of my page are at the same point now. Okay, all right. Ooh, Chris, what's the next algebra step? Yeah, divide this down. Yeah, exactly. So in my variables, it happens to be twice the height. That's what it would be. So I can say final velocity squared minus initial velocity squared divided by twice the height of the cliff will always tell me the answer, what is the gravity field of the planet. Okay, so there's the general solution, true for everybody. Now with the numbers, divide that over. Gravity field is whatever 540 on 110 is, and that's going to be, well, it's going to work out to meters per second squared. So 540 on 110. Okay. And I get gravity field is 4.91 meters per second squared. Hey, you guys remember before we went plugging and chugging, we're saying, does it look like weak or strong gravity field? I think that's relatively weak compared to Earth. It sure is, isn't it? Isn't that about half of Earth gravity? Yeah, it sure is. Sure is. Let me make sure that's an answer choice. It's yep, it's right there. Right there. But there's still, we got to figure out how much time. How much time did it take for the ball to reach the ground? How much time? Right. Oh, come to think of it, it sure does seem like a lot like the treehouse question we were looking at a few minutes ago, doesn't it? Right. Oh, which one do you want to pick? First, second, or third? Please say the second. Are you guys gonna say the second one? Right. Because could you solve it with the first one? The first one, if you use the quadratic formula, right? But we did that already today. So I wanted to do at least one of those, just to make the point that you could. Let's do the second one because that one's faster. So let's go final velocity equals initial velocity plus acceleration times time. All right, solve for time now. Oh, split my paper again. You guys can see both versions of this. So I can go the crash velocity is equal to the throw velocity plus gt and solve for t this way. I could go plug in my known values. I know it's crashing at 24 meters per second. I know I threw it at 6 meters per second. And by this point, I know what the gravity field is because we just found it. It's that many meters per second squared. And times t, bring it all together. Boom, boom, just like that. Okay. In terms of variables, say I could subtract over the v naught, and that's gt. In terms of numbers, guys, 24 minus 6, what is that? 18, or I should have asked you guys what you do, but you guys are getting better and better in algebra, right? You guys would have subtracted over first. Right, it's 4.91 t. And then can you, what's the next step? Divide down that gravity field. Right, so the general solution is this. This will be the answer for everybody. And then over here, in terms of numbers, well, it's whatever that fraction is. 18 divided by 4.91. Okay. I got meters per second here. I got meters per second squared here. Okay. Ooh, guys, does the meters and the 1 of the seconds cancel? Okay, and 1 divided by 1 divided by seconds, seconds comes back out on top, which tells me 3.67 seconds. Had an answer choice, might be an answer choice. It's 3.6. Oh, yep, that's an answer choice. All good, all good. All right, you guys set? You set? All right. So yeah, it's about class time today. I'm gonna hang up this recording, but you got a little spare time. Walk around, answer any questions you guys have, and play guys some hot time videos. And yeah, you guys have this paper ready to turn into the gray tray on Tuesday.